Alright, today we're going to be learning a couple different strategies to help us solve exponential equations. In these first few examples, we're going to be solving by rewriting the exponentials, both sides of the exponential equation to have like bases. So with a problem like this, if we're going to solve it this way, what we want to try to do is find a base that the two bases that I have can be rewritten in terms of. For example, I have a base of 4 and a base of 64. I can rewrite both of those in terms of 2, or as a base of 2. So for example, the 4, I'm going to rewrite as 2 squared, but then that's still being raised to the 1 minus 2x power. Now 64, you may not know what exponent on 2 is equal to 64, but we can figure it out. If you think about 64 in terms of its factors, it's equal to 8 times 8. And maybe we know that 8 is 2 cubed. So this would be 2 cubed times 2 cubed, or we could rewrite that as 2 to the 6th, because of course when you're multiplying like bases, you add the exponents. So this 64, I'm going to rewrite as 2 to the 6th. Now if you look on both sides of the equation, they both have a base of 2. And so if 2 to the 2 times 1 minus 2x is equal to 2 to the 6th, then hopefully it makes sense to you that the exponents should be equal to each other. Now over here on the left, I have an exponent being raised to another exponent. So I'm going to multiply those. Power to a power, you multiply the exponents. And that's going to be equal to 6. And here now we just solve it like an algebraic equation. I'm going to distribute the 2 and get 2 minus 4x equals 6. And then I could subtract 2 from both sides. And negative 4x is equal to 4. And then divide by negative 4. And we end up with x is equal to negative 1. So pause the video for a moment and try the next example on your own. If you were successful on this next example, you should have ended up with negative 18. So again, I had bases of 8 and 16. I rewrote them both in terms of 2. 8 is 2 to the 3rd, 16 would be 2 to the 4th. And once we have like bases, we can set the exponents equal to each other. And then you just distribute and solve for x. From that point, it's just your algebra skills that you learned in Algebra 1. Let's look at the next example. Here we have 5 to the 4x minus 1 is equal to 1 over 125 to the 2x plus 5. Again, I'm trying to get like bases. And on the left, my base is 5. And 5 is a prime number. I can't rewrite it in terms of any other base, so 5 is going to have to be my base. On the right, so I'm going to keep the left the same. On the right, I want to write 125 as a power of 5. And so let's do a little math. 5 times 5 is 25. And then if I multiply by 5 again, 25 times 5 is 125. So 125 is 5 to the 3rd. And then we're still raising that to the 2x plus 5 power. Now, if you remember, when I have a base with an exponent in the denominator, I can rewrite that as a negative exponent. And if I do that, then I end up with 5 to the negative 3 to the 2x plus 5. Now I have both sides of my equation with a base of 5. And since my bases are the same, I can set my exponents equal to each other. And now we solve for x. On the right, I'm going to distribute that negative 3. And then, let's see, I'm going to add 6x to both sides and add 1 to both sides. And 10x is equal to negative 14, and then last step, divide by 10, and x equals negative 1.4. So again, pause the video and try the next one on your own. On the next one, if you were successful, you should have ended up with x equal to 14. So here with our bases of 1 over 27 and 1 over 9, we rewrote both of those in as a base 3. 1 over 27 is 3 to the negative 3, and 1 over 9 would be 3 to the negative 2. And then set my exponents equal to each other and solve the equation from there. Let's look at the next example. In these last examples, we're going to use logarithms to solve the equations. Because, like in this first example, we have 4 to the x equal to 98. There's no like base out there that I can rewrite those terms as. 98 cannot be written as an exponent on 2. And so we need to use another strategy, and it's going to be logarithms. Now, we've talked in class about how logarithms and exponentials are inverse operations, which means they undo each other, which is very important when we're solving equations. If I have an exponential like 4 to the x, which we have here, in order to undo that to get x by itself, remember my ultimate goal here is to find out what x is equal to. I need to get it by itself. But in order to do that, I need to get it out of the exponent. So to undo the exponential, I'm going to use a log because that's the inverse operation. And here's what that looks like. We're going to log this side, and specifically I'm going to use a log of base 4 because the base of my exponential is 4. I need these two bases to match each other. So log base 4 of 4 to the x. And of course, if I take the log on one side, I have to do the same thing on the other. So I'm going to log base 4, 98 on the right side. Now, here on the left, if I have log base 4 of 4, those undo each other, or they cancel out, and I'm left with x is equal to log base 4 of 98. And if you want to get a decimal approximation for that, you can put it in your calculator, and it is approximately equal to, let me do that again, approximately equal to 3.307. But if you don't have a calculator with you, you can just leave it in the log base 498 form. That's fine. Pause the video and take a moment to try the next one on your own. If you were successful on this one, you should have ended up with log base 18 of 73. And again, you can leave the answer in that form. If you prefer a decimal answer, that's approximately equal to 1.484. And the way that we did that is we just took log base 18 of both sides to cancel out that base and get the x out where we could solve for it. Let's look at the next example. So I do have an exponential again, but in order to use a log to undo that exponential, I need to have the exponential, the base and the exponent, all by itself, with nothing else being added or subtracted or multiplied from it. I need to have this expression by itself. And since I'm multiplying by 10, what I'm going to do to get that by itself is I'm going to divide by 10. I'm going to undo the multiplication with division, divide by 10 on both sides, and now I have 3 to the 3x is equal to 9.6. Now I have the exponential by itself, and at this point I can use a log to undo the exponential. So I'm going to use log base 3 of 3 to the 3x. That's a lot of 3's there. And if I do log base 3 on the left, I have to do the same thing on the right, because of course if we do something to one side of an algebraic equation, we have to do the same thing on the other side. Now on the left, the log base 3 of 3, those cancel each other out, and I'm left with 3x is equal to log base 3 of 9.6. And now final step, to get x by itself, we're going to divide by 3 on both sides, and x is equal to I should say approximately equal to 0.686. Pause the video, try the next one on your own. If you were successful on this one, we should have ended up with log base 19 of 39 divided by -5. And if you have a calculator available, you could get the decimal approximation, which is -0.248. So what we had to do on that problem, similar to the one before, except this time we were subtracting 6 instead of multiplying by something. And so you can see here at the top that I added 6 to both sides. Then I had the exponential by itself, and so we take the log of both sides at that point to undo the exponential, and then I have -5x equal to log base 19 of 39. And from that point, divide by -5 to solve for x. We've got one more example, and this time notice our base is e, so I've thrown in that special base, which means to undo it, we're going to be using the natural log. Again, I need to get the exponential term by itself, and an exponential involves only a base and the exponent. So it's only that part. That's what I need to get by itself. So first step, I'm going to add 6 to both sides. So -3e to the 5 minus 8x is equal to -54. And then next up, we're going to divide by -3. So I have e to the 5 minus 8x is equal to +18. Now I have my exponential by itself, and so I'm ready to undo the exponential. Since my base is e, I want to use a log base e, which happens to be the natural log. So natural log of e to the 5 minus 8x, and of course if I natural log the left, I have to natural log on the right. On the left side, the natural log and e undo each other, and I'm left with 5 minus 8x is equal to the natural log of 18. And now we solve for x. I'm going to subtract 5. -8x is equal to, now be very careful here, we cannot subtract that 5 from the 18. The 18 is included with the natural log. So we need to just subtract 5 out on the end like this. Our final step would be to divide both sides by -8. And if I do that, I'm going to move over here. We end up with x is equal to the natural log of 18 minus 5 divided by -8. And again, we could put that in our calculator and get a decimal approximation, which would be, give me just a moment, natural log of 18 minus 5 divided by -8, approximately 0.263. So one more time, pause the video and try the last one on your own. If you were successful on this one, we should have ended up with log of 32 minus 1 divided by -5. And if you have a calculator, that approximation comes out to -0.493. Now let's go back and look at our work. From the beginning, we were trying to get the exponential term by itself. And remember, an exponential is a base and its exponent, and that's all. So I needed to subtract just subtract 11 from both sides, and then divide by -2. At that point, we have the exponential by itself, and we can natural log both sides. Again, we're using the natural log because that's the log whose base is e. From that point, you end up with 1 minus 5x is equal to natural log of 32, and then it's just a matter of getting x by itself, subtracting 1 from both sides, and then dividing by -5.